This is M1, section 14, momentum and impulse, on page 43 of the M1 notes booklet. As usual, this is a video, not a lesson, so you may need to pause in order to take notes. I won't be pausing as I would do in a lesson to give you time. Right, so first of all, impulse is equal to force times time. But that's not the only version of impulse that exists. So if we're actually writing it as a formula in letters, we would probably write I equals Ft. Now, from the constant acceleration equations, the Suvat equations, V is equal to U plus AT. Now we can rearrange that to T equals. So AT is equal to V minus U, divide by the A, T is equal to V minus U over A. And we can replace that in the impulse equation. So impulse is equal to force times force times time replaced with V minus U all over A. Now from Newton's laws, force is mass times acceleration. So impulse is equal to mass times acceleration times V minus U all over A. The A's cancel out. So impulse is equal to the mass, m, times V minus U, in brackets. Multiply that out, impulse is equal to mv minus mu. Now impulse is also force times time, so Ft is equal to mv minus mu. Now mv and mu are examples of momentum. So momentum is mass times velocity, and they are measured in Newton seconds. Impulse is also equal to Newton seconds. So we have impulse is equal to the change in momentum, because u is the starting velocity and v is the final velocity, or force times time. So both those definitions are equivalent, and we can often use both in the course of an exam question. So in this example, we have a particle mass 7 kilograms at rest on a smooth horizontal surface. A horizontal force of magnitude 5 newtons acts on the particle for 8 seconds. And we're to find the final speed of the particle. So in this case, we're using both definitions of impulse. So impulse equals force times time. So the force is 5 newtons. The time is 8 seconds, so force 5 newtons, time 8 seconds, times them together, and the impulse is 40 newton seconds. Then we move to the other definition of impulse, being change in momentum. We know what the impulse is, it's equal to 40. We know what the mass is, it's 7. Want to find the final speed. Minus 7, the initial speed it was at rest, so rest means the initial speed is 0 meters per second. So we end up with 7 times v equals 40, divide by the 7, and two significant figures, we get 5.7 meters per second. And so we use both versions of impulse to find out an unknown. So in this case, a ball of mass half a kilogram hits a vertical wall with a horizontal speed of 50 meters per second. So let's do a little sketch. It's often useful in mechanics. So before, we've got our ball with mass half a kilogram, and it's doing a horizontal speed of 50 meters per second. After it hits, it rebounds, so it's going in the opposite direction with a speed of 40 meters per second. The mass is still the same, half a kilogram. And we're to find the magnitude of the impulse exerted by the wall on the ball. So very often we're asked for the magnitude of impulse, because impulse is a vector quality, so you might get, say, a negative answer if you've chosen right positive, or vice versa. So very often they ask for the magnitude of impulse, so if you get a negative answer, we then have an extra line showing the magnitude without the negative value. So in this case, we haven't got anything about force and time, so we're using impulse equals change in velocity. Now we have to be careful here, because if we're making right positive, then u is equal to 50. Now u and v are velocities, not speed, so the fact that the 40 is going to the left is important, so that would make the v minus 40. The mass is a half regardless, so we have, in this case, we get half times minus 40, take away a half times 50, so minus 20, minus 25 gives minus 45 Newton seconds. Now, as I've said, the minus just indicates direction, so the impulse is acting to the left. We want the magnitude of impulse. So in that instance, we ignore the negative sign. So, final example, at time t equals 0, a particle of mass 10 kilograms is moving with a velocity of I plus j meters per second. 4 seconds later, its velocity is 3I minus 2j meters per second. I want to try and find the constant force acting on the particle. So again, we can use the impulse equations. So we start with, we can calculate impulse using change of momentum, because we have the information for that. And this time we're going to get it as a complete vector quality, not just a simple positive for right, negative for left, but in terms of I and j. So the mass is 10 times the final velocity, 3I minus 2j, minus the mass of 10 times the initial velocity of I plus j. So multiplying out, we get 30I minus 20j, take away 10I, take away 10j. Collecting like terms, we get 20I minus 30j Newton seconds. So that's the impulse. Now we want to know the constant force acting on the particle, so we'll be using the other version of impulse, force times time. So 20I minus 30j equals, force is unknown, the time, but it took 4 seconds for this to happen, so 4 times F, divide both sides by 4, and we get the constant force. So 20 divided by 4 is 5, 30 divided by 4 is 7.5, so we get 5I minus 7.5j, and the force is measured in newtons. And that concludes this section.